All right, so now we're on chapter 2, limits and the derivative, section 3, continuity. So this is an important section, but it's really going to be more background, looking at functions. Eventually in chapter 2, what I really want to get to, which is not too far off, is getting to application problems. Here's a revenue. We have to see how revenue is changing, so we take this thing called the derivative. But in order to really understand derivative and really understand stuff, we have to go through these first sections to kind of get some background. So it's important stuff, but not the most important stuff, I would say. So informally, a function is continuous over an interval if the graph can be drawn without moving up pen or paper. So if you can draw a graph and not lift up your pencil, then that's a graph that's continuous over an interval. So if I was going to graph the function x plus 2, I can simply draw that graph, never have to take my pencil up. That has continuity throughout. Okay, so again, you're like, that's nice. And then what we looked at before was this little thing called limit as x approaches 2. So as we approach 2 from the left and as we approach 2 from the right, you'll see that it goes to the same answer, 4. And if we plug 2 into the function, we get 4. So kind of reviewing a little bit of what we went over last time, what that limit idea is. Now, if along that graph there's a break, there's a problem, there's a hole, there's something going on, then we say it's discontinuous. So if I had the function x squared minus 4 over x minus 2, well, I'm drawing my graph, and then all of a sudden, I find that there's a hole, okay? And what we should be getting good at, the background stuff, is why is there a hole at 2? What's special about 2? 0 in the denominator. What's happened when you get 0 in the denominator? Undefined error, but undefined is what happens. There's a hole there. There's a problem. Are we okay? That's the background stuff. That's what they really try to push here. But again, reviewing what we did last time, as we get to 2, the limit as h approaches 2, what number is it getting close to? 4. The limit coming from the right, what number is it getting close to? 4. So the limit as x approaches 2 from either side is 4. So it looks like something nice is happening. But what happens when you plug in 2? It's undefined, so the function at 2 is undefined. Are we okay? So again, the limit is getting closer and closer, but not plugging in. That's what we're spending time on last time. Another example of a discontinuous one is looking at the absolute value of x over x. Notice we're moving along, and then at 0, it jumps up here. It's undefined at 0, and then it continues. That's another example of discontinuous. Not everything is continuous. And if we're talking a little bit of review last time, as we approach 0 from the left, as x approaches 0 from the left, it approaches -1. But coming from the right, it approaches 1. So the limit does not exist. And if you try to plug in 0, you can't. So it's undefined. So that's kind of the stuff we did last time. Now we're just building upon it a little bit. So a function is continuous at the point x equals c if the limit exists, f of c exists, and the limit of c, f of x equals f of c. So it's continuous if all 3 things happen. And a function is continuous on the open interval a or b if it's continuous at each point on the interval. So knowing just what continuous means. Question? So 1, 2, or 3. So here, the limit has to exist. Both sides, it's going to a number. 2, you can plug in a number and you get an answer. And those 2 match. So the limit from the left and the right are approaching 4. When you plug in the number, you get 4. That side equals that side. 4 equals 4. Okay? And if one or more of the conditions fails, then it's discontinuous. So looking at this graph, let's look at -4. Okay? So basically, this is kind of reviewing what we did last time. So if we look at -4 all together, coming from the left, what number is it approaching? Coming from the left, what number is it approaching? 2. Coming from the right, what is it approaching? Is that a problem? Okay, so does the limit exist at -4? No. Okay, that's part 1. Part 2, If you plug in -4, what do you get for an answer? Is it the open or is it the filled in? If you plug in -4, what do you get for an answer? The filled in, which is 3. Okay? Those are the pieces that we should know. So coming from the left, you get 2. Coming from the right, you get 3. Do they match? So does the limit exist as x approaches -4? Doesn't exist. That's one part. And that's what we did last time. We should be good there. A separate question is, when I plug in -4, what do you get? 3. So those things don't match. We have discontinuity, which we can already see it's not continuous. There's a break there. Okay? And so in order to say that, we have to review what we did last time. So let's look at another one. Okay? I want you to look at -2. Okay? So on your paper, I want you to write down this. I'm going to write it down, and I'm going to bounce back and forth. So we're going to see the limit as h approaches -2 from the left. What do you get? I want to know the limit as h approaches -2 from the right. Do that first. And that's going to tell us the limit as h approaches -2. And then I'm going to simply ask you a totally separate question. What happens when you plug in -2? So write that down first, then I'll bounce back to the picture. So this is review of last time. The limit as h approaches -2 from the left, what do you get? The limit as h approaches -2 from the right, what do you get? And then if these numbers match, it exists or doesn't exist. If it doesn't exist, you're done. If it exists, what number is it? It should be the same number. And what happens when you plug in -2? What happens when you plug in -2? So this is kind of reviewing last time, making sure it makes sense. And here's the graph. Okay, so look at -2 coming from the left, what is it approaching? Look at -2 coming from the right, what is it approaching? Then, does any limit exist or doesn't exist? If it doesn't exist, you're done. If it exists, what number is it? And then a totally separate question, what happens when you plug in -2? All right, so let's start slowly. Looking at -2 coming from the left, what number is it approaching? 5. So that first part, 5. Second part, coming from the right, what is it approaching? 5. So the limit from the left, 5. The limit from the right, 5. Do those numbers match? Yes. It exists where? 5. So that should be 5, 5, 5. We good? Then, totally separate question. What happens when you plug in -2? Uh-oh, open circle. What does that mean? Undefined. So, what does all that mean? Building on last time. So we got 5. We got 5, and we got 5. But when we plug in here, we get undefined. So, is it continuous or discontinuous? Is it a continuous graph? No, you already knew that from the beginning. There's a hole there. Because there's a hole, it's not continuous. Okay? So yes, I know the answer from the beginning just by looking at it, but this is reviewing our last time to prove it. 5, 5, 5 doesn't exist, therefore it's not continuous. Okay? Do the same thing at 1. See if you can figure out what the symbols look like I'll show you in a minute. But what will the symbols look like? It's the same thing. And here are the symbols. So the limit as h approaches 1 from the left, what number is it? The limit as h approaches 1 from the right, what number is it? And the limit as h approaches 1, sorry. And then what happens when you plug in 1? Let's talk about it. So, first of all, if you're a little shaky right now, you're like, I'm getting a little confused. Let's make sure we fully understand what we're talking about. Here's one. Can I draw this without taking my pencil up? Can I draw this without ever taking my pencil up? No, you have to take your pencil up, right? So is it continuous or discontinuous? Okay, that's the answer. That's it. We're done. We know. But what we learned last time is a way to check that. Coming from the left, for 1, what number is it approaching? 4. Coming from the right, what number is it approaching? 1. Okay, that's last time stuff. So coming from the left, we get 5. Well, it should be 4. That's a typo from them. That should be 4. Coming from the left, what is it approaching? 1. Because they don't match, does the limit exist as x approaches 1? Does not exist. Okay? So if I go back to the paper, this is 4, 1, does not exist. So we already have a problem. We know it's not continuous. Okay? Then we take it one step further. We can also check what happens when you plug in 1. Can you plug in 1? Why? What do we have at 1? Whole, nothing there. So it's going to be what? No, it's not exist. So we know it's not continuous. Okay? We're going to do this last one together. We should be getting good at this now. The book likes to give a lot of examples. So let's talk about 3. Coming from the left, the limit as x approaches 3 from the left. What number do you get? What number do you get? 3. Coming from the right, what do you get? 3. So does the limit exist? Yeah. Yes, at? Boom. That's where we should be at right now. What happens when you plug in 3? There's a problem. They don't match. So is it continuous? No. That's it. That's it. That's it. Sometimes we look at something, and I know on the screen it looks pretty crazy, but it's not. That's my job to kind of make sure it all makes sense. But if you can do all this, left, right, middle, left, right, does limit exist, plug in a number, then you're exactly where you need to be so far. If it's shaky, you have to go back and watch those videos, watch this video, check out the notes again. Okay? So, use the definition of continuity to discuss the continuity of the function at the indicated point. So if I want to plug in, if the function is x plus 3, what happens when you plug in 4? What do you get? 7. Okay, so that part works. That's the bottom part. Now, the limit coming from the left, the limit coming from the right, this is a line. Isn't this a line? Are lines continuous? Yeah, so it's going to work. So just by knowing it's a line, I know if you want to find the limit as x approaches 4, you're going to get 7. If you plug in 4, you get 7. Everything matches. Therefore, it is continuous. Okay? So we're getting a little faster. I don't even need the picture anymore. Let's look at the next one. So this is a line. It's continuous, and we verified it. If I show you the function x squared minus 9 over x plus 3, and I say, is it continuous at -3? What does your gut tell you right off the bat? What's the problem? Yeah, you can't plug in -3. Does that make sense? So you already know there's a problem. So can you plug in -3? Nope. Right off the bat, it's not continuous. So it's not continuous. And if you plug in -3, you get 0, 0, which we said before is indeterminate. But right away, we broke one of the rules. We know it's not continuous. Okay? What about this one? H of x equals the absolute value of x minus 1 over x minus 1. Is it continuous at 1? Is it? Can you plug in 1? What happens? You get 0. Can you have 0 in the denominator? Nope. Is it continuous at 1? No. That's it. Let's not overcomplicate it or make it weird. But we already know that it's not continuous at 1 because, number 1, if you try for the limit, it's going to be 0, 0, which means we got to look further and it's not defined, and we can't plug it in. Okay? So again, I know that this seems complicated, but it's background stuff, and you should be okay. So we have to look at it from the left, we look at it from the right, and if it's continuous, it all should match up. So if two functions are continuous on the same interval, then if you add them, the difference, the product, the quotient are continuous as well for the same interval, except to make the denominator 0. So all this stuff we've been talking about in chapter 2, you just got to be careful, especially when you're dividing by 0. That's like the big aha. Okay? So if your function is just a number, it's continuous. So if you had a function of 5, it's just a straight line, that's going to be continuous. If your function is a positive integer, it's continuous for all of x's. So if you add x to the 3 or x to the 2 or x to the 1, all those are going to be continuous. Okay? A polynomial function, it's continuous. Rational function, be careful. That's the part we're dividing. And anytime you divide, you can't have 0 in the denominator. And then as far as square roots, as long as the inside is positive, if we have an odd integer greater than 1, then it is continuous wherever the function is continuous. But if n is an even positive integer greater than 1, then it's continuous where it's non-negative. And all this simply means here, can you take the square root of a negative? No. But can you take a cube root of a negative? Yes. That's why if it's odd, it's okay. If it's even, you got to be careful. Okay? So, to make this really quick, you have 3x squared minus 5x plus 8. At this point, all of you know what shape is that. That's a problem. Is it continuous? Yeah, done. That's it. That's it. That's it. We can check it with all the rules, but that's all we really have to worry about. It's polynomial, it's continuous. Looking at this one, already you have a gut reaction. Is it continuous everywhere? It's just called rational, right? It's being divided. Is it continuous everywhere? Can I plug in any number and it's going to work? So is it continuous? No. It's continuous except for which places? Which places? 3. Why 3? What's 3 minus 3? 0. Can you have 0 in the denominator? That's it. That's all you have to remember, right? So it's continuous except for n1. -1 or 1? -1. So this would be continuous except for 3 and -1. Why? It makes the denominator 0. Okay? That's the huge point that's coming through. Here, the polynomial, the number inside, x squared minus 9 is a polynomial function, so yes, it's continuous. Because this is an odd number, it's continuous. If it was even, we'd have to be careful because you can't take the square root, fourth root of negative. Yep.
How can radical of 0?
How can you what?
Radical of 0.
Square root is, yeah, but just be careful. But we're not worried about the 0, we're worried about like all. So basically, let's take a picture of this. And anytime you get a little stuck, let's talk about pictures. So for this one in particular, I'm going to go to math, y equals math number 4, cube root of x squared minus 9. And I'm going to hit zoom 6. And let's just look at the picture. Is it continuous everywhere? Yeah, that's all we're worried about. And for the cube root square roots, the part that you need to focus on is number 1. Inside the x squared minus 9, that is a polynomial function. It's continuous. But where you have to be careful is if this wasn't cube root, this was square root, it's got some restrictions. Okay? So if I had the square root okay, look what happens when I do the square root of x squared plus 9. Is it continuous? Nope, it's got restrictions. We okay? Good questions. Oh. And again, this one, it's a square root, so we have to be careful. So the polynomial function of x plus 1 is continuous, but since the n, it's a square root, is even if it's continuous of values when it's greater than -1, which is the interval from -1 to 0. For example, -1 is okay. Anything greater than -1. -1 and greater. But if I graph this one, square root of x plus 1, is this continuous everywhere? From -1 on. Not always. Okay? So, a sign chart is a basic tool for analyzing graphs in calculus. This will be very extensively in later sections. We'll use continuity properties to develop a similar effective procedure for constructing sign charts. So basically, we're going to show you how a sign chart can be helpful to solve a problem. So I'm going to jump right to the problem. Okay? So here's the question. Solve the inequality x plus 1 over x minus 2. And I want to know, when is that greater than 0? Are we okay? But here's what the whole point of everything. Look at this. You already know there's an issue. Where there's an issue. What number can I not plug in? 2. Okay, so there's an issue at 2 because it's a rational function. You got that. But I want to know, when is this graph greater than 0? So instead of trying every single number in the world, we can start by looking at important numbers. So important number one, what can x not be? 2. That's an important number. Okay. Another important number for a rational function is, what would make the top 0? -1. So those two are important numbers. And so what we do is we can make a number line to find out when this is true. Now again, you can solve this like you did in algebra. This is just giving you the idea of a sign chart. Sign chart may be useful to you, may not be useful to you, but it's something they want to explore. So can you plug in 2? Nope. Circle. Can't be 2. An important number is -1 because it makes the top 0. And yes, you can have -1. So a sign chart is saying, instead of just picking numbers at random, I use these as like my intervals. I'm going to pick a number over here, pick a number over here, and pick a number over here, and see what happens. So let's go to your calculator. Everyone go to your calculator. And let's have our calculator help us out. So we go to the calculator. We go to y equals. In y1, let's put parenthesis x plus 1, close parenthesis, divided by parenthesis x minus 2. Now, we're going to do a couple things. Number 1, we're going to graph it in the standard window. So I'm going to hit zoom 6 to graph it in the standard window. Okay? Now, at this point, all this background stuff is to understand this graph, okay? First of all, at 2, is there a problem? And what is the problem called? Now that we've done all this work. What do we have at 2? We have a vertical asymptote. And again, adding the limit stuff. The limit as h approaches 2 from the negative side, from the left side, is approaching what? Negative infinity. Coming from the right, what does it approach? Positive infinity. We know there's something going on, but that infinity stuff means we have an asymptote. It's exactly where we're at, okay? My question is, when is the graph greater than 0? Greater than 0 means above 0. So I can answer this question for you right now just by looking at the graph. What number is this? -1. Was that one of our special numbers? Yep. So the graph is above 0, anything less than -1. Are we okay? The graph is also above 0 where? Anything after 2. So anything after 2, the graph is above 0. 0, above 0, above 0. So I already know the answer just by looking at it. If it's less than -1 or greater than 2, less than or equal to -1, greater than 2, the graph's above 0. So I can answer this graphically. Yep. Yeah, so this is 0. Where is the graph above 0? It's above 0 here, and it's above 0 here. It is below 0 here and here. Are we okay? So what does a sign chart do? A sign chart basically says, if we go to table set, second window, everybody has Ask Auto, right? We did this a couple times. Make sure it's Ask Auto. A sign chart basically is giving you without graphing, a way to do what we just did. Go to the table feature, second graph. The points are -1 and 2. So let's pick a number less than -1. Any number you want less than -1. Less than -1. -2. When you plug in -2, your result is 0.25, but more importantly than that, is your result positive or negative? Positive, greater than 0. Now, pick a number between -1 and 2. What's a number between -1 and 2? 0. When you plug in 0, your result is negative, below 0. Now pick a number greater than 2. 3. Your result is positive, greater than 0. So the same thing we did graphically, they're doing by plugging in numbers. So we go to our sign chart. And they show us in this sign chart that anytime you plug in a number less than or equal to -1, you're going to get a positive result. Between -1 and 2, you're going to get a negative result. And after 2, you get a positive result. So if I want to know when is the graph greater than 0, when will that happen? That's going to happen at the positives. Between -infinity and -1, and between 2 and infinity. So the sign chart idea is to help you figure that out. If the sign chart is helpful for you, fantastic. If you can do it by graphing, fantastic. If you need to kind of work it out, this is a good strategy to help you figure that out. And you're probably like, okay, I kind of get that. I need one more example. Well, guess what? We have another example. We always have another example. So the definition of real number is a partition number for a fraction is discontinuous. So that whole idea of discontinuous is those numbers that make it discontinuous, or numbers that are important, are going to be our partition, the numbers we use. So we find the partition numbers, we find the numbers that make it discontinuous, all numbers that the function is equal to 0, then we plot it, divide into intervals, and then we test numbers. And then looking at results, we can answer our question. So this is our last one. We're going to take a little time on this one. A bakery estimates its annual profits from the production of sales of X loaves of bread per year is given by PX dollars, where the profit is PX equals 6X minus 0.001X squared minus 5,000. For what values of X does a bakery make a profit selling bread? Okay? let's take this slowly. I'm going to write this down. So we have P of X, I'm going to put it in order, negative 0.001x squared plus 6x minus 5,000. Okay? So here's our profit function. X is the number of loaves, and P of X is our profits. Okay? Now, the question this had was, when am I making money? When am I making profit? So to answer that question, profit is when this equation is what? When are you making profit? When the equation is positive, which means greater than, perfect, greater than 0. Okay? So I'm going to make a sign chart and figure out what works. Now again, I can graph this and get the answer right away. I'll show you how to do that. A sign chart is just another strategy, and they'll use it a little later. So I'm going to give you a little bit of help by factoring this for you, which is probably the part that'll give you the most difficulty. But I'm going to go ahead and factor this for you. So I took care of the factoring for you. And after factoring this, you are now able to tell me the special numbers, the important numbers, the numbers that give me 0. And what would be my special numbers? 1,000 and 5,000. Stop there. Is everybody okay? Now, the idea of a sign chart would be find your zeros, numerator, denominator, find all your zeros. Those are called our partition numbers. Then we make a little chart. Here's 1,000. Here's 5,000. And my job is to find when is the graph going to give you greater than 0. So I'm going to pick a number over here. I'm going to pick a number over here. And I'm going to pick a number over here. Now, I'm going to fill in the 1,000 and 5,000 because those are numbers that work. They give me 0. They're not great numbers. I don't want to make 0 profit, but they do work. They're not undefined. When it's undefined is when I fill in the circle. Okay? So let me stop there for a second. Any questions on how I got that? Yep.
So the only way to undefine is if it's a rational number.
Yep.
And you put 0 on the top.
Yep. Perfect. And that's something that always shows up. Like there's your vertical asymptotes. That's where it's discontinuous. It's something that shows up as a problem a lot of times. Vertical asymptote, undefined, discontinuous, it's all the same stuff. It's an issue there. Okay? So let's go to our calculator. Let's go to y equals, and let's just type in our original. Negative 0.001x squared. Okay? Plus 6x minus 5,000. Now, you're going to do this on your own. What you're going to do is you're going to take that, go to your table feature, plug in a number less than 1,000. Tell me if you get a positive or negative. Plug in a number between 1,000 and 5,000. Tell me if you get a positive or negative. And plug in a number after 5,000 and tell me if you get a positive or negative. again, any number you want, as long as it's in there. About 1 more minute. Okay, so I go to my table. What's any number less than 1,000? Any number you want. 500. Do you get a positive or negative? So in this area, it's going to give me negatives. Okay, what about a number between 1,000 and 5,000? 3,000, 2,500, all of them are great. You're going to get what? Positive. And then what about a number greater than 5,000? 6,000. You're going to get a negative. Now, I don't know about you, but if you want to do good business, do you want to make money or lose money? Make money. When will you make money? When will your profit be above 0? 1,000 to 5,000. Now, I don't want to make no money, so we put parenthesis, parenthesis. Because at 1,000, you make no profit. At 5,000, you make no profit. So when will you make profit? Between 1,000 and 5,000 in parentheses, because if you put brackets, that's no money. So 1,000 to 5,000 in parentheses. That's it. Now, question. Absolutely. So what I'm going to get you next is, let's graph this thing. Well, guess what? If I want to graph it, the very first thing you need to do is hit window. What's my x going to be from 1 to 1? Well, we can start with, again, I make profit from 0 to 1,000, right? And so we're going to plug in maybe 0 to what? 0 to 10,000? Counting my thousands? But then what about my y? Well, I would go to my table feature and look at the numbers we're talking about. If I go from 0 to 10,000, and the numbers in between were like 1,000, 5,000, 2,000, 3,000, what kind of numbers am I talking about here? We know 1,000 and 5,000 is 0. Anywhere between goes up to about what? 3,000, 4,000. So how high should we go to be careful? So my y, let's go from 0 to, let's do 6,000, counting my thousands. And again, let's talk about it. Let's talk about it. If you graph it, okay. First of all, this is 0. When is my graph above 0? From 0 to 5,000. Does that make sense? If I looked lower, if I made my y go from like negative 2,000, let's just say, after 5,000, you lose money, negative results. Before 1,000, it's below 0. Are we okay? So all that can be checked in a calculator. This is just giving you another way. Okay? And that's it. That ends 2.